Okay, guys, so we're going to be on pages 8 and 9 talking about verifying identities with trig functions. And you're going to see that this is actually similar to what we did previously, which was simplifying. Now, there's one big difference between simplifying and verifying, is that verifying problems have an equal sign. And that gives us an end goal for the problem, right? I know what I'm starting with and I know where I'm supposed to end up. Whereas with simplifying, we really didn't have an end goal. We were just working until we thought we were done, until we had finished it, okay? So verifying, these problems have an end goal. Whereas simplifying, we knew that those were just problems where we were trying to work our way to the smallest possible situation. Okay, so let's take a look at what that means. So if we look at number 8, this is the bottom of page 8. Okay, and it's asking us to verify the identities. Okay, and we have 1 over 1 minus sine theta plus 1 over 1 plus sine theta equals 2 secant squared theta, okay? And they've given us some hints. They said, well, first of all, we're going to need common denominators because we're adding two fractions together. And they tell us, hey, what is different about this problem compared to all the previous ones? And hopefully what jumps out at you is actually this equal sign is the big difference. And how we verify something is that we only work on one side. We take that one side and transform it into the other side using the identities that we know. And by turning that side into the other side, you've now proven that these are equal, and that is how you verify the identity. Okay. One key fact is, guys, we always want to start on the more complex side, right? That's where we'll work, and then we'll turn it into the simpler side. So if we took a second and we said, let's look at this problem, and let's see which side is more complex. Hopefully you're going to catch on that this is my complex side, okay? The left-handed side that has all of the signs and the fractions in it. And on the right-hand side, we can call this the simpler side. So I'm going to take the red side and turn it into the blue side. And that means my goal for this problem is going to be this. I want to end up at 2 secant squared theta. Okay, so once again, my ending goal for this problem is the other side of the equal sign. It is 2 secant squared theta. All right, so that's where I want to end up. Let's see how we'll get there. So the first thing my hint tells me on here, it says, hey, get common denominators. So I'm going to take the left-handed denominator to the right-handed side, and it's got to go top and bottom. Okay, can't just do it on one side, got to be top and bottom. And we'll do the same thing on the other end. We're going to take this denominator from the right and bring it to my left-handed side, 1 plus sine theta. So now we're going to go ahead and distribute all of this out. So it may get a little bit messy at first, but luckily for us, the top part is pretty simple. 1 plus sine theta, 1 times each of those. 1 on this side is going to be 1 minus sine theta. Right? These are going to be added together. And let's look at these denominators, okay? These denominators might be a little bit ugly. So we're going to need to take this and FOIL, okay? So if you've forgotten how to FOIL, pause for a moment and go look up how to FOIL out an expression, okay? Remember, it means first, outside, inside, last, okay? So multiplying the first two numbers gives me 1. Then I've got the outside two numbers, 1 and negative sine squared, so minus sine theta. Sine times 1, the inside numbers. And sine times sine is going to give me minus sine squared theta. And we have the exact same numbers on this side. 1 minus sine plus sine minus sine squared. And I'm running out of room a little bit. So let's go ahead and see if any of this will work out to be a little bit simpler. And the first thing that pops out is in the denominator, I've got minus sine theta and plus sine theta. Let's get rid of those. Same over here. These are going to cancel out. So my denominator overall is now 1 minus sine squared theta. Ooh, a lot better than what we had written there. Okay, let's look at the top bit. Is there anything we can do with this top part? And I see 1 plus sine theta and 1 minus sine theta. So these two sines are going to cancel out, and I'm going to just have 1 plus 1, which is going to give me 2. Okay, let's continue to simplify this now. Let's keep in mind our goal. Okay, my goal is this 2 secant squared theta. No fractions. There's no plus or minus signs in there. So my first thing is I see this square, and that's kind of giving me the red alert. Why don't I try using a Pythagorean identity? So what's going to happen is this statement right here is going to become cosine squared theta. And if you're not sure how I'm getting that, let's take a look at that identity. So my identity for this was sine squared plus cosine squared equals 1. And by moving that sign to the other side, I'm going to get it to match up perfectly with my expression in the problem. So I'll have cosine squared x equals 1 minus sine squared x, which this section right here is what I'm replacing right there and making it into cosine squared. So this was using the Pythagorean identity. And from now, let's keep that goal in mind again, right? In case you guys forgot, my goal is supposed to be 2 secant squared theta. So I'm kind of on the right track. This is getting smaller. I'm getting closer to it. My last step is going to be to turn cosine into secant, okay? And there is an identity for that to move it to the other side. So the next identity I'm going to use is my reciprocal identity. And that identity connects secant and cosine. So 1 over cosine is equal to secant. Okay, and all I have to do is say I'm going to move this to the top and switch it to a secant instead. So now this cosine squared is going to move to the top, and it's going to now be a secant squared theta. And so finally, right now, I've gotten to this 2 secant squared theta, which is equal to the goal that I had set initially when I started this problem. So you can look back, you can see, hey, my goal up here was 2 secant squared theta. So I reached my goal, and I'm going to go ahead and put my little check mark that I reached that goal. So what are we looking for in this problem? Okay, we're looking for, starting from the yellow, can you break it down and cancel things out and work it so that you get to this statement that these are equal? In this case, you can see, guys, it actually took me a couple of different identities. I ended up using the Pythagorean identity first, and then I used the reciprocal identity to change this in a couple of different steps. Okay, but the first thing was I started with the complex side. I combined it together to start making it into the simpler side. And it slowly came together until I was at a point where I could turn it into the final goal. Okay. The reason that we always want to start on the complex side, all right, is because it's much easier to make things simplify and cancel out rather than trying to work your way backwards from the simple side to the complex side. Okay. So one big rule I want to point out to you guys: never work on both sides when you're verifying. Okay, guys, if you work on both sides, that is kind of like cheating the problem. Okay, you've broken some rules. Verifying means you start on one side and you turn it into the other side. Don't ever change both sides, otherwise, you've immediately made that problem incorrect. Okay, so the previous problem was a little bit intense. It involved a lot of multiplying and using identities and stuff. Let's see another example. So the first thing we need to do is choose which side to work on. Okay, so which of these sides looks more complex? Take a second, look at the problem, pause if you need to, and try to pick a side that looks more complex. Hopefully you picked that the tangent x plus cotangent x was the more complex side. Okay, and the reason for that is because actually this is two different terms. Okay, so that's the side I'm going to work on, tangent x plus cotangent x. All right, and the other side that is only a single term, right, that is going to be the side that I'm going to leave alone. That is secant x cosecant x. And I'm putting parentheses around it because otherwise it reads horrendously. All right, so this is going to end up being my goal. Secant x cosecant x is my goal. All right, so when I simplify, that's what I'm looking to end up with. All right, let's see what we can do. Now, my first thought is, can I turn tangent or cotangent into secant or cosecant? And nothing's really clicking to me right now, especially because they're not squared, so I can't use the Pythagorean identity. But thankfully, they gave us a nice hint over here. And the hint mentions we can go ahead and turn everything into sines and cosines. So sine and cosine are kind of the building blocks for all of the trig functions and their identities. So imagine this as trying to break everything down into the smallest pieces and then rebuild it from the ground up. Okay, now this can be kind of messy. It's a little bit brute force, but it will work for us in this case. All right, so let's start with tangent x. Tangent x in terms of sine and cosine is going to be sine x over cosine x. All right, and cotangent x is going to end up being cosine x over sine x. All right, so now that we've turned these into sines and cosines, let's see if we can't combine it together a little bit more. Before I can add these two together, I'm going to need something. Do you remember what that is? If you said common denominators, great, you're on the right track. I know I'm going to take the bottom denominator here and bring it to the other side. And again, we've got to do this on top and bottom. And we're going to do the same thing, vice versa. We'll bring the right-hand denominator, sine x, up to the other side. So we'll do times sine x times sine x, top and bottom. So let's see what we've got so far. Sine times sine gives me sine squared of x plus cosine squared of x. And on bottom, I've got sine x cosine x. Just touching each other, they're multiplied together. All right, let's see where we're going next. I already see something funny happening as I put these two together. And let's go ahead and just line these up as a single piece. So I've got sine squared x plus cosine squared x over sine x cosine x. And this top bit is starting to look really, really familiar to me. I don't know why. Does it look like one of the identities that we've been using a lot? This is going to actually just end up equaling 1 because of my Pythagorean identity. And it reads, once again, sine squared plus cosine squared equal to 1. Okay, so I see sine squared plus cosine squared, and I jump some hoops and say, yep, that's going to be equal to 1. And I've got sine x cosine x at the bottom now. All right, some good news, guys. This is all one term now. It's still kind of a funky fraction, but it's all in one place. And what was my goal again? Let's take a look. My goal was to reach secant x, cosecant x, right? So let's see if we can get there. Are there any identities that will turn sine into a different one of those? Or how about with cosine? There are actually perfect identities for this using the reciprocals. Okay, so the reciprocal for sine, 1 over sine x, is going to be cosecant x, and 1 over cosine x is going to be secant x. Okay, so you can find both of those on your formula chart. So what we'll do is we're going to actually take each of these. This is going to move up, and this is going to move up, and each of them is going to turn into secant and cosecant respectively. Okay, so now what do I have left? Secant x, cosecant x. And there you go, guys. We've reached our goal. We know that we have solved the problem. Okay, once again, what are we looking for? We're looking to turn this yellow piece, my starting function, into that final end goal that we set to begin with. Okay, in the process, I used a Pythagorean identity and a reciprocal identity, two of them in fact, to change my pieces into the ones I wanted. Okay, how about another example? Now this one's a bit of a doozy. It can be a little challenging to tell, hey, which one of these is more complex? And there's only one little thing that's kind of going to push me in the right direction. And what jumps out at me, guys, is actually the squared on the left-hand side. Okay, that's squared. Because it's squared, it makes it still more complex than the right-hand side. Okay, so I'm going to go ahead and tell you guys that's my goal. All right, I want to try and end up here. Let's set that goal. All right, and we're going to go ahead and work on the left-hand side. So I've currently got cotangent squared y over 1 plus cosecant y. And I'm kind of looking at this and wondering, well, do I have any way to break this down or change it into other pieces? I could get a little crazy and try to make everything into sines and cosines, but that seems a little messy. Again, this square is going to give me a little bit of a gut reaction here, okay? The square tells me that I can probably use a Pythagorean identity to help me here. Sheet, the Pythagorean identity reads as cosecant squared theta equals 1 plus cotangent squared theta. And if I just move some things around, I'm like, okay, I just want this cotangent by itself. So minus 1. I've got cosecant squared theta minus 1 equals cotangent squared theta. So let's replace this cotangent with 1, or cosecant squared minus 1. And now you may look at me kind of funny and say, why would we make this more complicated than it already was? Because now this is starting to look uglier than what I started with. I still need to just find a way to break this down further. And this part may seem kind of strange to you, but I see this is squared on top, okay? And again, I'm like noticing this is kind of like a quadratic, even though it's got a cosecant in there. So what I'm gonna do is I'm gonna think, wait, what if I just pretended like that was x? And I'm gonna break it down via everyone's dreaded word, factoring, all right? So if you don't remember how to factor, guys, this may be a good time to go back and review. You can always run into a factoring question here, okay? So I'm going to pretend like this piece says x squared minus 1, all right? And this is one of my special factoring rules. It turns into x minus 1 and x plus 1, okay? It is the difference of two squares. because cosecant in this case is squared, and this is like a 1 squared. Okay, so that is breaking down, and now I've got this cosecant y plus 1, and that's going to be times cosecant y minus 1. Divide that by 1 plus cosecant y. And I'm going to see if there's anything that cancels out now. I'm seeing, hey, 1 plus cosecant and 1 plus cosecant down here. Let's go ahead and cancel those out. All right, and now what am I left with? Let's slide this up and see what we've got left. Cosecant y minus 1, okay? And again, just so that we don't lose track of it, my goal is to end up with 1 minus sine y over sine y. Okay, so I need everything in terms of sine. Is there an easy way I can turn cosecant into sine? I'm hoping you came up with that reciprocal identity again, and you saw that, hey, cosecant y right here, let's make that into 1 over sine y minus 1. And I can combine this by making common denominators again, right? So I'm going to treat this 1 as being 1 over 1 and multiply it by sine over sine. And that's going to end up giving me something I can put together. So over here, I've got 1 minus sine y on top over sine y on the bottom. And take a look, guys. That's actually my end goal. We made it. All right. So let's recap real quick what identities we did and what process we went through. So we started out with the problem up at the top, and we changed cotangent into cosecant first, okay, using this Pythagorean identity. Now, having done that, I saw a quadratic at the top and said, what if I factored that down? And by factoring this down, we got pieces that would cancel out with my denominator. I crossed those out, and I ended up with something a lot simpler looking that I could then change into signs to get to my end goal. Okay, so verifying is very similar to simplifying in that we're still using the identities, still trying to cancel stuff, still trying to combine stuff. But the good news is now, guys, you actually already know what your answer is going to look like. You know where you're trying to end up. Okay? Sometimes there's a little bit of an extra step where you're like making something change from cosecant into sine, like we did here, using that reciprocal identity. But overall, the nice thing is that we already know what the answer should be, and all you're trying to do is find a way to get to that point. Okay, I hope this video helped you guys with verifying trig identities. Okay, there's a lot more practice in your book. Make sure that you keep practicing this. There are a lot of patterns that you need to start recognizing. All right, before I go, let me note a couple of things that can help you when you verify or simplify. Okay, guys, so this last bit is just me pointing out some strategies that you can use to help you verify, and they also actually apply to simplifying. Okay, so the first one up in green, you can see I wrote that squares often use Pythagorean identities. Okay, squares are a great sign that you might be able to use a Pythagorean identity, which usually helps you consolidate or change one of your functions into something more useful. All right, something to keep in mind. Sometimes they come with a plus or minus 1. Okay, so these have a plus or a minus 1 sometimes. All right. The next thing I've written for you in red, it says, when all else fails, make everything into sine and cosine. All right. Making things into sine and cosine can be messy, but a lot of times you'll find different places that you can consolidate and cancel stuff out. Okay. Imagine it's like you can't find your homework in your backpack, so you dumped everything out on the floor. Sure, you made a mess, but you're going to find your homework eventually because of that. All right. And in blue, the last thing, work on the complex side. Guys, this applies to verifying. All right. You have to work on the complex side, and you cannot work on both sides. Keep your goal in mind, guys. Whatever was on the other side of that equal sign, that's where you're trying to end up. Okay. Sometimes you find yourself at the answer and you keep going trying to simplify it further when you don't need to. I hope these hints help you guys with verifying and simplifying these trig identities and expressions. Okay, make sure that you practice this. The only way that you get better is by practicing these. Okay, a lot of it is pattern recognition. All right.